This next video is on finding general solutions, also known as infinite solutions, with a calculator. So as we go throughout this unit, these instruct you to use a calculator, but you will not be told to use a calculator unless it says solve by graphing, which then you would just include a sketch of what you see on your TI-84. So we're going to revisit the first equation that we looked at, which was sine of x is equal to 1/2. And we already had found that our solution is pi over 6, 5 pi over 6, and then due to the period of 2 pi, works for sine, so we'll use plus 2 pi k. But how will this look in the calculator? So if you go to y equals, we have an equation, so we'll set y1 for sine of x, and then we'll set y2 for 0.5. Now, the window we will always use is 0 to 2 pi, even though this is a general solution problem, but obviously we can't set it to infinity, so we take a sample, and then from there we are able to see what solutions we have. And sine oscillates between -1 and 1, so I'll use -2 and +2. So if we get a sketch of this, we can see that there are in fact 2 points where they intersect, which is the pi over 6 and 5 pi over 6. And then because sine is periodic, we know that this will also repeat for infinity. So if I expand my window to 4 pi, I should see 4 solutions. And then at 6 pi, we'll see 5, 6 solutions, okay? And this goes on forever and ever and ever. However, the issue that students run into sometimes is that they'll try to use the calculator for every single problem. This is not efficient because if I find the intersection, I'll just use this one here. It's going to give you a decimal value, which we want exact values, which is why we use the unit circle. So the 2.617 is the 5 pi over 6. So you can use this as a way to check your work, but you have to recognize that if you truly want to see that, and since I just traced in the graph, if I do second answer, my calculator saves it. I can compare it to 5 pi over 6 and see that it is equivalent. However, if you just write 2.617, that's an approximation, which is not the exact, and you have access to the exact answer, that's not fulfilling the problem completely, okay? So use exact as much as possible, and if you only rely on the calculator, it's going to take you a long time to figure out the answers for these, okay? So I also want to go back to looking at the other equation. And if we look, we have sine of 2x, which equals 1/2. We also looked at this one in the beginning and found that we ended up with 4 solutions from 0 to 2 pi because of the 2 inside of the input. This 2 is a horizontal compression, which means we are squeezing more of the curve into the 0 to 2 pi domain restriction. So I'm going to keep sine of x here, and then I'm going to include sine of 2x for y3. So sine of 2x is the black curve, and then sine of x is the blue curve. So if we see now the new period for sine 2x is going to be pi, so we end up with twice as many solutions. So we should see the red line and the black curve intersect 4 times, which we do. Okay, so I'm going to clear out the original one, and we end up with this. Again, 1/2 is on the unit circle, so we are able to figure out what our solutions are from this, the exact answers at least. So if I apply the inverse trig, I end up with 2x. And we're solving for general, so I'm still going to use the plus 2 pi k. I have my original pi over 6 and 5 pi over 6, plus 2 pi k. From here, you can either divide by 2. I'm going to multiply both sides by 1/2. And this isolates the x. And then pi over 6 times 1/2, we get pi over 12. 5 pi over 6 times 1/2, we get 5 pi over 12. And now we see that horizontal compression being applied. Instead of solutions occurring every 2 pi, they now occur every pi, which is why we see 4 solutions in our window. Now for this one, we are able to get the exact answers because we started with solutions that were standard on the unit circle. So this would be my general solution. Right? I have my original 2, and then if I add pi, I end up with the next 2 that I see in my window. So this is how we'll set it up. But what if the domain restriction is from 0 to 2 pi? Okay, Now from here, you can use the calculator to see, oh, we do have 4 solutions, but also you should notice with that 2, we have a horizontal compression with a scale factor of 1/2. So that's going to double the amount of solutions that we have from 0 to 2 pi. So what we're going to have to do is I'm going to start with my pi over 12. And I can see that my next solution from pi over 12 will be a pi away. Okay, so I'm going to add a pi to that to get whatever that third solution is. However, we want a common denominator, so it's easier to combine these two terms. So pi with a denominator of 12 is going to be equivalent to 12 pi over 12. Okay, so now I can easily add these two fractions and I end up with 13 pi over 12, which is the third solution that we see in our TI-84. Okay. And then if I add another 12 pi over 12 to that, I end up with 25 pi over 12. And my domain restriction is 2 pi, which would be 12 pi over 24. Sorry, not 12 pi over 24, 24 pi over 12. And again, I'm writing everything in terms of 12 because my denominators are 12 for my original 2 solutions. So it makes it easier to see, oh, when am I leaving the domain of 0 to 2 pi? And because 25 pi over 12 is greater than 24 pi over 12, we will not use this solution. So once I finish with the first solution set, I move on to the second, which is 5 pi over 12. And I will apply the same algebraic manipulation that I did for the first one. So I end up with 5 pi over 12 plus 12 pi over 12, and I end up with 17 pi over 12. So this is where, even though I'm dealing with standard angles on the unit circle, the calculator will help because I have 4 solutions and I see 4 intersections in the calculator. Therefore, I know that these 4 would be my solutions if the domain restriction was 0 to 2 pi. Okay. All right, so from here, finding solutions in a restricted domain with a calculator. And this is solving by graphing. So if you see solve by graphing, there's no algebraic manipulation unless you are using your reciprocals, secant, cosecant, and cotangent. Because we don't have buttons for those on the TI-84, we will have to use the reciprocals for those. But for this first one, that's not necessary. So on the calculator, go ahead and clear out this. In Y1, I'm going to type in -3 sine x. And then Y2, we have cosine of x over 2. And again, window should be 0 to 2 pi. And if I look, my sine has an amplitude of 3, which means I need to adjust my window. Or you can do zoom fit, which this would work for this. So let's see what that looks like. So zoom 0. Okay, and that includes the extrema for the sine. Okay. Zoom fit will be an issue whenever you have asymptotes, but because I know sine and cosine do not have asymptotes, I can do zoom 0, and it will fix my vertical window for me. So if you're in the course at Plano East, we require that you draw a quick sketch. It doesn't have to be perfect, but we just want to see what you're seeing so that we understand how you're getting your information and how you're answering the question, okay? So within this one, there is one single intersection from 0 to 2 pi. And if I do second trace, find intersection, and I'll hit enter, 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 I end up with 3.14. So x is equal to 3.141. Now, hopefully you recognize that is just pi. But because it's a calculator app, if you gave us 3 decimals instead of writing pi, you would still receive the full credit for that. Okay. So the second one, now we have a reciprocal, also some asymptotes. We have 1/2 secant x is equal to sine 2x. So how I want to type this in the calculator is I'm going to reciprocate the trig, but everything else will stay the same, including any coefficients and anything with the input, okay? So I'm going to create my fraction bar. I have a 1 in the numerator and then 2. That's my 1/2. And then I'm going to have my cosine in the denominator. So if you look at this, nothing else has changed except for the fact I'm using cosine for secant, so I'm going to have cosine in the denominator. I didn't change it to cosine. I'm rewriting secant in terms of cosine, so we're still going to see those asymptotes because it's in the denominator. And then we'll have 2 sine x. Now, because this has asymptotes, you'll want to adjust your window on your own. And I can see that we have an amplitude of 2, which is good because my y min is -3 and my y max is +3. So we can go to the graph. This one's a little bit more complex, but we can still easily see the intersections. We will have 4 of them. So for my quick sketch, we have the secant here, and then down here we also have secant, and then the last part of secant here. And then for our sine, we have 2 intersections over here, 2 more down here, and then we're approaching a second one, but we never quite get there within our domain restriction. So again, your sketch, don't waste too much time on your sketch. We just want to see what you're seeing and how you're reading that data and answering the question. Okay, so x is going to be equal to, we'll do second trace. I'll do the first one, but you've been tracing for a couple years now, so you should be comfortable with at least doing this part. We're going to get really close to that first one. Enter, enter, enter. And I end up with 0.261. Okay. If I do this 3 more times, the second one is going to be 1.309. The fourth one is 3.403. Sorry, third one. And the fourth one is 4.451. So remember, College Board will accept, you can either truncate the decimal, so I have 0.261, or you can round up to 0.262 depending on that 4th digit. Either one is acceptable. Part C, we have 5 sine of 3x over 2 is equal to 2 secant x minus 1. So y1, we're going to go ahead and type in 5 sine. I have my fraction bar. We'll do 3x over 2. And then we have to use another reciprocal identity. Now we have that 2. I'm going to create my fraction bar, but the 2 goes in the numerator. And then in the denominator, I will have my cosine, and then my input will stay with my cosine. So again, we're not rewriting secant. It's still secant. We're just using the reciprocal identity and having cosine in the denominator. And notice that my input stays with cosine, okay? It will still be, yes, it looks like it's in the denominator, but x minus 1 is part of the term cosine. So it will go with cosine when we write that reciprocal identity. Now I can also see we have an amplitude of 5 and a vertical stretch of 2 for the secant. So I'm going to go back to my window, and I'm going to do -6 to +6. So I always do one more than what the largest stretch is, because sometimes there might be an intersection at the extrema, and you might not see that unless we can go beyond just a little bit of what the curve is showing. All right, so again, we'll have 4 solutions. And a quick sketch, I have my sine. We have a maximum, minimum, maximum. And then secant, we have 2 solutions over here, and then 2 more in the lower part, and then a little bit of a curve here. So again, we'll have 4 solutions, and you can use the trace function in this, the intersection. And when you do that, you should end up with x equals 0.351, 1.720, 2.993, 3.906. All right, so that is what we expect you to do for solve by graphing. There should be no algebraic manipulation, no moving side to side, no isolating. These are very, algebraically to solve these, we'd run into a lot of issues, which is what we will talk about in the next lesson, and why it's so difficult to solve these just by using algebraic manipulation. All right, so part 2, there are going to be 2 parts. It says solve for all solutions, general solutions, and then solve for each one algebraically from 0 to 2 pi. Whenever you're solving for 0 to 2 pi, you always want to do general solutions first, because just like this example, you could end up with 4 solutions, but if we were to stop here and exclude that repetition, you would be missing 2 of your solutions because you're not applying that stretch correctly or that compression correctly, okay? So we always solve for general first, and then we solve for the restricted domain of 0 to 2 pi if necessary. So this one, we have cosine of x over 2 is equal to 0.56. This is not a solve by graphing, so we will be using algebraic manipulation to solve it. Eventually we will come back to the calculator, but you should not be doing that until the very end. So 0.56 is obviously not a standard angle on the unit circle, but if I think about 0.56, it is positive, and cosine is positive in quadrant 1 and quadrant 4. So if I apply my inverse trig, because we already isolated the trig, so now we'll isolate the input. This is part A. We'll have x over 2. Actually, let me go ahead and show this step. I'm not going to show it every time, but this way we get an idea of what we're doing. So I have inverse cosine of x over 2. and that is equal to inverse cosine of 0.56. So obviously on the left side, the inverse will undo cosine, so I'm left with x over 2, which is equal to inverse cosine of 0.6. Now, this is the exact value. If I type it in the calculator now, I end up with an approximation. And again, the output for inverse trig is going to be an angle because my input is a coordinate. That's an x value in here. And that output being an angle represents this angle here. So inverse cosine of 0.56 represents this angle. So now what we have to do is using inverse cosine of 0.56, I need to represent this second angle, which is here. Now, looking forward, part A, you can use negative angles if you want to, but part B, we do have a restriction from 0 to 2 pi, so I want to plan ahead and make sure that I can use this solution set for part A and for part B. So I need a positive theta. If I just use negative cosine or negative inverse cosine of 0.56, I end up out of my domain restriction. So instead, I'm going to use my x-axis. My second angle is going to be 2 pi minus that slice because I'm in quadrant 4. And that slice is inverse cotangent of 0.56. Now these occur every 2 pi because cosine is periodic. So I'm going to add my plus 2 pi k at the end. So I'm still working with the exact values, okay? And we're using 2 pi because it's quadrant 4. Now, in class, I said if it's in quadrant 4, it'll always be 2 pi minus. It depends on the angle. Like if we end up with an angle where it places us in quadrant 3, that's going to be a different story, okay? So you really have to pay attention to how big your slice is and then what coterminal angle are you trying to find using that slice. And when I say slice, I'm talking about, I call it like this a slice, and this is also a slice. They are the same size. So I'm using those slices to find coterminal angles. All right, so now we're going to multiply everything by 2. So I end up with x is equal to, and then I end up with 2 times inverse cosine of 0.56, and then 2 times 2 pi will be 4 pi, and then minus 2 times inverse cosine of 0.56, and then we'll close the bracket. 2 times 2 pi k will be 4 pi k. So we have that horizontal dilation with a scale factor of 2. So now instead of compressing more solutions in, we are stretching them out so that when we do 0 to 2 pi, we will end up with 1 solution instead of 2 because we're cutting those solutions in half by stretching out cosine. So once I have my x isolated, that's when I can go to the calculator and start getting my approximations. This is the best approximation we will get because we waited until the very end to do it. So I have 2 times inverse cosine 0.56. That will give me 1.952. And this is the solution in quadrant 1, so the white piece. And then for my next one, I will do 4 pi minus, and I'm just going to copy it from up here, so we get 10.613. Close the curvy bracket, and then we have plus 4 pi k. So this is our general solution. Part B, the domain restriction is from 0 to 2 pi. Now we're working with decimals. These are still radians, all right? Radians can be in decimals, like pi is a radian, but it's 3.14. So we are still working within radians, but it's just that we are in decimal form. So I want to rewrite my domain restriction so that it matches the form that I'm in. If I do 2 times pi, I end up with 6.283. So my domain restriction is 6.283 in decimal forms. Again, still radians. Now, I said before, you don't want to rely on the graph, but you can use it as a resource to see how many solutions you will have from 0 to 2 pi. Why does it keep skipping like that? There we go. So if I type in, I have cosine of x over 2, and then I have 0.56. My window is still 0 to 2 pi. I'm going to do zoom 0. If I look, from 0 to 2 pi, I only have one solution, all right? There's only one solution. And if I think about that, it makes sense, because if I look at 1.952, that is within my domain restriction. But if I add 4 pi to this, pi itself is 3.14. If we multiply that by 4, that's going to be like 12 something, which means we will be out of our domain again. So I only have that one solution, 1.952, using that first solution. Now, if I think about 10.613, that is already out of my domain restriction because of that horizontal stretch with the scale factor of 2. Therefore, we only have one solution, which is 1.952. So this is a great example. Anytime you're solving for restricted domain problems, you should always solve for your general solution first, and then figure out how many solutions you have from 0 to 2 pi. Don't just ignore the repetition of these trig expressions, because if there's a horizontal compression, you're going to have more solutions than you see in the curvy brackets. E is going to be cosecant of 3x is equal to 5. So we recognize that this is a reciprocal. We are more comfortable working with our original 3, sine, cosine, and tangent, so go ahead and use the reciprocal. So I'll have sine of 3x is equal to 1/5. And I'm doing this because I reciprocated the right side. I will also reciprocate the left side. Now, people try to do this. Sine of 1 over 3x is equal to 1/5. And we have to get rid of this bad habit now. So in inverse trig, I went and asked another teacher about this, and she explained it really well. In inverse trig, if I have inverse sine and I reciprocate that, let me restart this. So what if we started with inverse cosecant of 3x? And we're like, oh, we are more familiar with inverse sine, so I'm going to reciprocate it. So I'll end up with inverse sine of 1 over 3x. This happens because this is a coordinate. So remember SOHCAHTOA, that is our coordinate. That's our, for sine, it would be opposite over hypotenuse for the triangles that we create within our unit circle. So that's why these reciprocate, because we are flipping the coordinates on the unit circle. However, for sine, that is not the coordinate. This is our theta. 3x is an angle, and our sides are now over here, opposite over adjacent, which is why we're flipping that one now, because it's opposite of the actual trig expression. So be careful with how you reciprocate. In these, we aren't dealing with inverse trig right now, except for when we are evaluating to set up our solutions. If we are using the reciprocal in the beginning, you have to flip the opposite side, not the input, because the input's a theta and your opposite over hypotenuse is over here. Because for cosecant, this is hypotenuse over opposite, so it's 5 over 1. So when we reciprocate, we end up with opposite over hypotenuse. All right, from here we have 1/5. So 1/5 is not a standard angle, but it's when sine is positive, so we'll use that to our advantage. So when I apply arcsine, I have 3x is equal to, I'm going to have arcsine of 1/5, and then that is our slice that is in quadrant 1, so it's this one. Arcsine of 1/5 will be this angle here. Now, if I want my slice in quadrant 3, I need to use arcsine of 1/5 in order to get what that exact slice will end up being. So if I'm in quadrant 3, I can use my x-axis. I have pi here, and if the entire angle that I want is this minus the slice that I found in quadrant 1, okay? So we'll do pi minus arcsine of 1/5. Close the curvy bracket. And let's make this a little bit smaller so I can fit everything. There we go. And then we'll do our plus 2 pi k at the end for sine. All right, so now I'm going to multiply everything with 1/3. So we end up with x is equal to, our first one is going to be arcsine of 1/5 divided by 3. And then 1/3 times pi, I get pi. Actually, I'll just divide the whole thing by 3. Make it a little bit easier to fit everything in here. All divided by 3. Close the curvy bracket, and then I have plus 2 pi k all over 3. Is this still recording? Just want to check. Okay, good. All right, so now that x is isolated, I can go into the calculator, set up your fraction bar, alpha x, so I'll have inverse sine of 1/5, and this is all divided by 3. So we end up with 0.067. And then we'll repeat the process, fraction bar, second pi, minus, we'll end up with inverse sine of 1/5, all over 3. And we end up with 0.980, and then plus 2 pi k all over 3. So here is our general solution. All right, so going into part B, I can see that I have a horizontal dilation with a scale factor of 1/3. So now we're compressing it by a factor of 3, which means instead of 2 solutions, I'm going to end up with 6. Okay, we're tripling the number of solutions from 0 to 2 pi. So this is a little trick that we talked about in class. Instead of having to trace them or just do 0.67 and then adding everything, there's another way that we can do this in the calculator that I want to show you. So I'm going to take my 0.067, which is here. I'm just going to copy it. And I'm going to store this exact value. So I'm going to hit store and then alpha A, enter. So now I've stored it as A. And then I'm going to take my second one, which was the 0.980, enter. And then I'm going to hit the store key, alpha B. So now I have that saved as B. And the reason I'm doing that is because I'm going to type it into Y1. I don't want to use the approximation, okay? I want to use the exact one from what the calculator gave me. So I'm going to go to Y1, and then I'm going to type alpha A, and then I can see that from 0.067, my next solution will be 2 pi over 3 later. So I'm going to do plus, I'll have my 2 pi, and then instead of k, we'll do x over the 3. And then I will do the same thing for the second one, which was the 0.98, so alpha b, plus, and then I have my 2 pi k over 3, or 2 pi x for the calculator. Now, don't go to the graph because it's just 2 linear functions. What you need to do is go to second table, and you can see solutions here. So it gave me the 0.0671, and then the calculator is adding that 2 pi over 3 for me, and then it adds it again, and again, and again, and again, and again. And we are able to see a list for both of these simultaneously, okay? So again, we are in decimal form for radians, so we'll go from 0 to 6.283. So I want to find all solutions in the red and blue column that are between 0 and 6.283. If I look at my first column, I see my original, the 0.067. Next, if I add 2 pi over 3 to that, I get 2.161. If I add 2 pi over 3 to that, I get 4.255. Add 2 pi over 3 again, I get 6.35, but that's above my 6.283, okay? So I'm done with this column, so I'm going to go to the next column. Next, I have my 0.980. Add 2 pi over 3, we get 3.074. Add 2 pi over 3, we get 5.168. And then if you add 2 pi over 3 again, you get 7, which goes out of our domain. So there is our 6 solutions for this. If you're like, I'm not going to remember how to do this, then just go back to the original screen, find your 0.6 or 0.067, and then from there, you can add 2 pi over 3. And then you'll get that second value. And then you can do it again, add 2 pi over 3, and so on and so forth. Just remember that you cannot go above 6.283, okay? All right, part F and the last example for this video is going to be 4 tangent squared 2x equals 1. So we'll divide both sides by 4. So I end up with tangent squared 2x is equal to 1/4. From here, we'll take the square root of both sides. So we end up with tangent of 2x. And then remember, taking that square root, we get plus or minus. Now, I'm going to split up this radical. So we have root 1 in the numerator, which is 1. And then we have root 4 in the denominator, which will just be 2. So we end up with plus or minus 1/2. Now, this is not standard for tangent on the unit circle. However, we will end up with 4 solutions. So we'll have a solution in quadrant 1, quadrant 2, quadrant 3, quadrant 4. Now, this setup is going to be a little different. I'm going to show you another little trick. This is part A, sorry. So we are using the inverse tangent, so we'll end up with 2x is equal to. Because the period for tangent is pi, we can go ahead and do inverse tangent of plus or minus, and I'm going to use the decimal 0.5. And then we'll do plus pi k. So what we're doing here is, with my inverse tangent, I have my solution in quadrant 1, which is positive 1/2, and then my solution in quadrant 4, which is negative 1/2. Because remember, inverse tangent, we don't always use this, but it has that symmetry. It exists in quadrants 1 and 4. So I have my positive theta here, and then I have my negative theta here using those inputs. And because of that symmetry, I can go ahead and rewrite my solution expression as this. So from here, we'll multiply both sides by 1/2 or divide by 2. So we end up with x is equal to, we'll have inverse tangent of plus or minus 0.5 divided by 2 plus pi over 2k, or pi k over 2. All right, so if I go on the calculator, I do inverse tangent of 0.5, I end up with 0.463. Now, if I do inverse tangent of negative 0.5, we get that same value, but it's just negative. So that's why I'm able to rewrite it like this. Divide by 2, and we end up with x equals plus or minus 0.232 plus pi k over 2. And this is our general solution. So this plus or minus will only work for inverse tangent and inverse sine because they exist in quadrants 1 and 4, okay? Part B, we will go ahead and find the solutions from 0 to 2 pi. So I'm going to save the, positive one because I'm going from 0 to 2 pi. So divide by 2, and now I'm going to store this as alpha a. And again, I'm going to come back to y1, and I'll have alpha a plus, and then I have pi x over 2. So pi x over 2. Go to my table. Second table. And again, I can see that I have this list ready for me. We see our first solution, which was the positive 0.232. And if I go up, I can see the negative ones. And then let's come back to here. So I have my 0.231, or 2, and then I have 1.802, and then next I have 3.373, and then 4.944, and then I see a 6.5, but that goes above our domain restriction of the 6.283, so those are my 4 solutions. All right, hope this was helpful.